What's up, mathematicians? Welcome back to our lesson on conditionals. In this video, we will look at how we can use Venn diagrams to better understand conditionals. So we'll start by looking at this conditional that we've been talking about in this lesson. So if in LA, if someone is in LA or lives in LA, then that person is in California. Another way to write this is in LA implies in California with this with this arrow implication symbol. Okay, so we have two sets that, if we look at this conditional, there's sort of two relevant sets that we can talk about. So one of those sets is people in LA. And the other relevant set is people in California, right? So we have the set of people in LA and the set of people in California. Now we want to understand the relationship between these two sets of people. And given this implication and given what we know about, I guess, reality, we know that the set of people in LA is contained inside the set of people in California. So we'll write that in this way. So people in LA is the smaller set, and that set is contained in a larger set of people in California. Okay, so anytime you have a conditional where you have the first part of the conditional implying the second part of the conditional, the first part of the conditional will be a subset, or at least can be represented as a subset of the second part. So it sort of moves outwards. So we start with the inner part, and if you're in the inner part, it implies that you are in the outer part. More abstractly, if we have the conditional if A, then B, which we can represent this, of course, as A implies B, then what we're saying is that A is a set wholly contained in a larger set B. Okay, and by the way, it doesn't have to stop just with these two sets, right? And we can grow our Venn diagram even farther. These two sets. Oh, and by the way, maybe I should mention this, that I understand that technically what I'm drawing here would probably be considered an Euler diagram, not a Venn diagram, but typically, these are taught as Venn diagrams. That's been sort of the standard way that they're referred to. So I'm just going to go with that because I feel like it actually causes more confusion to call these Euler diagrams. So we're going to call them Venn diagrams. And so we could have this set A inside B, and the set B could be inside some other set. Maybe that's set C. And we could continue on and on with this, right? And interestingly, this gives us some insight into, what's going to turn into a type of argument that we'll study later on in the next lesson, actually. So that if you're in A, it implies that you're in set B. And if you're in set B, it implies that you're in set C. And that can go on and on, right? So I could even write this in this way. So there's a sort of transitivity that comes with these implications. We're not going to talk more about that now, but it will show up in the next lesson. Now, if we wanted to write these as conditionals, we would actually need a second conditional here, right? So we would have to write it as if A, then B, if B, then C. But you can see here the Venn diagram is a pretty nice visual way to understand the relationship between these sets that isn't necessarily obvious when you're just looking at the conditional written out or even at this symbolic representation. Now, before we wrap up this video, let's talk about how this idea of logical equivalence shows up in the Venn diagram representation. So let's say we have some logical equivalence expressed as a biconditional. So I'll say A if and only if B. As we discussed in the last video, we could also write this as A with the implication arrow pointing both directions, B, meaning that A implies B and B implies A. These two are logically equivalent. So we have this set of all things A, and this other set, representing all things B. What is the relationship between these two sets? Well, if we look at this, we'll realize that everything in A must be in B. But because the implication goes the other way too, everything in B must also be inside A. So A is inside B and B is inside A. What that means is that we really just have one set. Okay? We have one set which is A and B. A and B are the same set in this case. So, for example, if you recall the biconditional I talked about in the last video about Los Angeles and California's largest city, if we have the set called, oops, I should have written people in, I'll write that. So people in LA, well, that is the same as the set of people in California's biggest city. So if you're in, so how did I phrase it? I think so. So you're in LA if and only if you're in California's largest city or biggest city. What that means is that if you're in LA, you're in California's biggest city, and if you're in California's biggest city, you're in LA, meaning these two sets are really just the same set. They're the same thing. And so that's what happens in the case of logical equivalence. So that will wrap up our lesson on conditionals. In the next lesson, we will look at some basic structures of arguments and talk about whether they are valid or invalid. As always, thank you so much for watching. If you learned something here, please do like and subscribe, and we'll see you in the next lesson. Bye-bye.